Great. So yeah, Juliet graduated from University of Wisconsin. She was part of Tristan Lécuyer's group, and she joined us in January to begin her postdoc with me at CCSR. And she's working and will continue to work on a project that focuses on inferring high cloud feedback using CloudSat Calypso observations and a little bit of Cirrus. And that project is supported by CloudSat Calypso funding. And today she will be mostly talking about her PhD work. And so that's it from me. So Juliet, you can take it away.
Great. Thank you very much for that introduction, and thank you all for attending this lunch seminar. I'm happy to be part of the GISS group here now, and I'm privileged to talk a little bit about one aspect of my PhD work that I did with Tristan Lécuyer. So I'll be focusing on telling you a little bit about the top of atmospheric cloud radiative effects of tropical convection from an A-train perspective. So why do we care about tropical deconvection and their radiative effects? This is here just an image of a deconvective system and a little bit about the details of a deconvective system is that there are updraft regions or deconvective cores that vertically transport energy and mass from the boundary layer into the upper troposphere. And for those of you who attended Andrew Gettleman's talk yesterday, he put it very succinctly and well that clouds are important or the radiative impact of clouds are important for a climate perspective. And so for the case of a deconvective system, clouds are predominantly cold and bright in Andrew's words. So they're cold because they reduce the outgoing long wave radiative emission from the Earth's surface. And the amount that they reduce is very much dependent upon how high these cloud tops are and also their cloud optical thickness. And so the taller and the thicker clouds, they actually reduce the long wave emission and contribute a warming if you're looking at their cloud radiative effect. Now you have the shortwave impact, and these clouds are bright, and so that means that they reflect a lot of the incoming sunlight, and their reflection is very much based on, again, how thick they are. And so the thicker the clouds are, the brighter they are, and the greater cooling impact they have at the top of the atmosphere. So a little bit more looking at the cloud radiative effects at the top of the atmosphere. We have the cloud radiative effects is just the difference in the alt sky and clear sky fluxes. And these figures from CloudSat Calypso NOTIS measurements of the radiative fluxes show that there is strong shortwave and strong long wave effects that actually cancel each other out in the tropics to contribute a near neutral effect. And in the tropics, you have a lot of these high clouds. And so the high clouds are what are mostly contributing to this near balance. And so, okay, there's this near neutral effect in the tropics, but a lot of people have been wondering, well, how might the cloud properties change due to the climate change, and then how might that feed back into influencing climate change? And that largely has to do with the radiative effects then changing in response to cloud property changes. So this figure here is just a schematic showing about a projection as to how tropical deconvective systems might be changing in a warming climate. So the red box is showing that modeling studies are moving towards an idea that deconvection is increasingly clustering into moisture regions, and these deconvective regions are intensifying, so they're getting higher into the atmosphere, and the anvil cloud amount is reducing in extent. And so that definitely has an impact on the top of atmospheric radiative effects. And so there have been some large uncertainties in climate models associated with these high cloud changes. Again, looking at this box in the red, that just shows the tropical band. Climate models do not adequately capture the radiative feedbacks due to changes in high cloud amount and opacity. We see this line in orange dictates the high cloud amount, and these dotted components of the line are low confidence, and then the high cloud opacity we see is mostly low confidence as well. And it's largely because it's really difficult to capture the importance of convective cloud properties to their radiative effects. And so these cloud properties and the radiative effects, they vary widely within a single convective system, which we have shown in the top figure, which is a vertical cross section from a radar reflectivity profile from CloudSat. And the bottom figure is the long wave, short wave, and net cloud radiative effects as a function of latitude. And you can probably notice that these lines are rather fine. So I'm just going to highlight all the different warming and cooling impacts within a single deconvective system. However, when averaged over the full system, the net cloud radiative effect is just a slight warming near neutrality. So that just highlights the complexity even within a deconvective system. Another feature too is that you have a lot of this underlying low-level cloud that's often present that can influence the radiative effect of these systems. So it's rather complex. And then you also recognize that the radiative effects and their cloud properties vary over the course of a single convective system life cycle. They are different in different environments, and they exist on multiple spatiotemporal scales. And so how do you really compare the radiative impact of an isolating deconvective system, perhaps if there's multiple deconvective isolated systems within a certain region compared to a large scale system. So we want to think about these deconvective systems and their cloud properties and radiative effects, not necessarily within these like large domain grid boxes, but rather think about them on a cloud object scale. So really trying to connect their distinct cloud properties, the relationships between those to their radiative effects. So for a given vertical intensity, we want to pretty much capture statistics on cloud top altitude, their cloud optical thickness, understand also that the frequency of convection is important for understanding the relative radiative contributions. And this is hopefully to provide some benchmark statistics for assessing their cloud properties and their radiative effects in a warming climate. And I also want to clarify that even though we are looking at these cloud, the anvil amounts for a given vertical intensity, we're not saying that for a given vertical intensity, this is the anvil cloud productivity, because as Greg Elsasser has studied extensively, and like other people have shown this, that the life cycle of a single updraft is a lot different than the life cycle of anvil cloud. So anvil cloud retains memory of previous deconvective cores and their intensities. This is more so just kind of what are the large scale statistics and connecting some of these cloud properties. So the focus of this work is to first quantify the total net radiative effect of tropical deconvection, and that takes into account how frequent deconvection is, how large these systems are, and then identify how important each cloud property is in influencing the top of atmospheric radiative effects of these convective objects sorted by vertical intensity. And I just wanted to say that this work is being finalized and will be submitted here shortly at some point, hopefully soon. So this is just a overview of I guess, the remainder of the talk. We've completed the backgrounds. I'm going to introduce the database of convective objects from A-train measurements that I created, and then go a little bit into the results. Part B, this linking cloud properties to their radiative effects, is going to be the bulk of the presentation. And then go a little bit into the future work and applications, and then just a couple slides on what I'll be doing here at GISS. So first of all, what is A-train? A-train is a constellation of low Earth orbiting satellites. They observe the Earth two times during the day, 1:30 a.m. and p.m., and they extend over nearly the full globe. It's really useful to be able to use multiple instruments on board the A-train, since they're making these coincident measurements. And so one of the instruments that we use is the cloud profiling radar on board the CloudSat, and this is very sensitive to cloud droplets. And it has a high vertical resolution, and also nearly a 1 by 1 kilometer footprint, and so that's able to detect deep convective cores as best as we can from satellite observations. And then we also supplement CloudSat measurements with the Calypso LiDAR to be able to detect thin cloud, which is very important for understanding the top atmospheric radiative budget. And then cloud radiative effects are calculated from CloudSat, Calypso, and MODIS-based observations that are used to derive radiative fluxes. And then here's just an example on the bottom right of a vertical cross-section of a convective cloud object from CloudSat. So this studying in a convective object framework has definitely started becoming a lot more popular. Even when TRIM was launched with these precipitating features, EdSibster did a lot of work with this. But shifting gears now to a more cloud-oriented approach, I'm going to introduce how we identify these deep convective objects from A-train. So if we take a cross-section or a CloudSat overpass, we identify all of the deep convective flags first. And how do we do that? Well, the cloud profiling radar is very sensitive to precipitation, and in fact, it attenuates when it encounters precipitation. And so here I just showed a couple of profiles, distinct profiles. One is in the convection region, which we denote by this blue line, and then stratiform region, which is this green line. And we see, if we take a look at this figure on the right, we have the height on the y-axis and the reflectivity on the x-axis. And this blue line, the convection region, shows that the reflectivity starts to decrease at around 10 kilometers in the atmosphere. However, where the stratiform region, the reflectivity decreases at around the freezing level or melting layer, whichever terminology you prefer. And so what we do is require that the attenuating signal must be at least 1 kilometer above the freezing level.
But
yeah.
in like the stratiform or in the anvil region, you also have a decrease that's elevated, but that's not attenuating. That's just a elevated reflectivity source.
Yes, yeah, that's true. So the attenuate, yeah, you do see, I think it's capable of being able to understand that that's not attenuation. That's a good point, but yeah, it's just elevated. Yeah, yeah. There's also a condition of peak reflectivity that needs to be met as well. Yeah, thank you. So then once we identify all the deep convective flags, we group them together. If they're adjacent to one another, we group them as a single deep convective core. If there's some separation between them, then they're multiple cores. And so then we connect all the cloudy pixels together using a Python scikit image function. It's a it's image identification package from Python, which is very useful and it automates the process. And we just require that the cloudy pixels, they have a reflectivity of at least negative 28 dBz. And then we also impose a cloud top height gradient threshold. So if the cloud kind of sharply cuts off, then we know that it's no longer deep convection. So for example, here, this object would be cut off right around here because there's a sharp decrease in cloud. And we know that this is a stratiform region. So here are two examples of these deep convective objects. So the top is showing a single core system. These black dots show that this is one single core, and it's really, really intense, you know, really high in the atmosphere. And there's a lot of attenuation right in that core. And then bottom is showing multi-core case that spans, this is wild, like almost 25 degrees latitude. And you're probably wondering, well, like, is that actually like physical? Like, is this dark shaded blue region is CloudSat or Calypso's detection of cloud. And I do want to note that it is rather challenging in trying to assess from these instantaneous snapshots whether this thin cloud is actually was actually formed from this perhaps synoptic event, or you know, if it is just a residual anvil from another system that kind of merged. So that is an added complication of these multi-cell or multi-core systems.
And that multi-core system was counted as like one convective object?
Yeah, it was counted as one convective object, yeah.
The Calypso is LiDAR, right?
Yeah.
So when you combine the two, there's some sort of translation between the LiDAR backscatter power and reflectivity. So I'd imagine like the former's like kind of second moment, and the latter's, you know, whatever it is, sixth moment or fourth moment for ice, I don't know. So there is some conversion there to put them on the same plot.
It's not that like so there's a CloudSat product, it's called 2B Cloud Class LiDAR that it combines CloudSat and Calypso measurements. And so what I do, it's a little bit simpler than what you do. And what I do is just fill the cloud base height and the cloud top height within a fake reflectivity of those, say like negative 30. And these cloud top heights are, you know, if Calypso identified the cloud there, then those would be present. And so that's what that is showing right there. Yeah. So now on to the first result component of just understanding the total net cloud radiative effect of these convective objects. We identified approximately 34,000 objects twice daily between about a little over 4-year time period. And first just showing the frequency of convective objects as well as their length scales. And we see that these objects, so the frequency is just the number of convective objects divided by the number of CloudSat overpasses within each grid box in this map. And at most, convection is, occurs about 15% of the time. And that's predominantly in the West Pacific warm pool, South Pacific convergence zone. And so they actually are rather infrequent. And the length scales are on the order of 10 to 100 or 1,000 kilometers, which is pretty consistent with previous studies of deep convection. And so those, yeah.
So is there any, for the length scale, you
Yeah.
just consider that pretty uniform, except that there's some noise, or do you think there are systematic, variations from one region to the other?
Oh yeah, there are definitely systematic variations. What's interesting about this plot is that, I didn't account for the number of systems that, let's see here. the frequency of occurrence of different length scales in this plot. But from other maps that I've created, I do notice over the maritime continent, there's a lot of these systems called superclusters that are kind of on the 1,000 length scale, like 1,000 kilometer scaling. And that is also like there's Bob Howes, who's also looked into that, and he deemed kind of like the supercluster mesoscale convective complex terminology. And yeah, I think it is actually kind of interesting that this is that this is picking up only on, or that it looks fairly uniform across here. But you do see some slight increase in lengths above the maritime continent. Yeah. So then taking a look at the total top of atmospheric radiative effect from convection, when we weight by the frequency and the length scales of these convective systems, we see that the bottom plot shows the net cloud radiative effect, and that on average, these objects generally contribute a small net cooling. Again, because convection is infrequent, but then also we see that there's a near cancellation between the long wave and the short wave cloud radiative effects, which is shown by the top two plots. And this is again averaged over both day and night. But we apply a normalization to the shortwave component to account for the variability in the diurnal cycle, because we're only able to capture the daytime, so the 1:30 p.m. Shortwave radiative fluxes. So we have to apply normalization.
Is this a calculation or is this from series?
This is a calculation. So this is from just the CloudSat, Calypso, and Modus derived radiative fluxes. Yeah.
Did you try to look at series?
I have looked at not exactly at these times of day, but I have looked at series measurements. And I am noticing some similarity. Yeah, I'm noticing similarity. But I need to do some more investigation in series, yeah.
So
The thing with series though is that it won't be able to capture the thin cloud, the radiative effects of thin cloud fully, but it would be good to compare to series what it sees. Yeah.
So do you see any day-night differences?
Sorry.
Day-night differences, given that you've got active sensors and you're looking at 1:30 in the afternoon, sorry, in the morning and 1:30 in the afternoon?
Yeah, in terms of the frequency of convection, especially over land, you see that convection is a lot more frequent during the daytime overpass, even though the 1:30 p.m. is at a minimum in the diurnal cycle of convection. We still do see that it's more frequent during that 1:30 p.m. than 1:30 a.m. Time. But then over the ocean, we do capture a little bit of the diurnal cycle of convection, where it's more frequent at that 1:30 a.m. overpass. Yeah. And then we can't, in terms of the long wave, anyway, that's kind of what we saw, what we see. And so then on to kind of the bulk of the results, linking cloud features and their radiative effects. We will focus on the varied or the deep convective mode of these convective objects. And we're gonna partition them between single cell and multi-cell systems. Let's see. I want to just ignore the ice only versus underlying liquid. We're not going to go into that for the sake of this presentation, but we will be focusing only on the daytime convective objects, because just to capture the shortwave radiative effect from those over a 10-year time period. And so now we want to kind of understand a little bit more about how the cloud properties influence their radiative effects. And so looking at how does cloud optical thickness influence it. As I mentioned at the beginning of the presentation, the cloud optical thickness influences both the shortwave and the long-wave cloud radiative effects. This figure here shows a simulation of cloud radiative effects on the y-axis versus the cloud optical depth on the x-axis, which we define as the cloud optical thickness. And it's simulated for high clouds at a cloud top pressure 440, less than 440 HPA. And we see that the shortwave or the long wave plateaus, it increases as cloud optical depth increases, but then plateaus at an optical depth between 3 and 4. And that's actually when the shortwave crosses over and is more enhanced than the long wave, which we see by the net cloud radiative effect. And so we identify kind of two regimes, this thin cloud regime, which we're just looking at the thinnest cloud, so the fraction of a deep convective system with the cloud optical depth less than 1. And then the thick cloud regime, which is the fraction of convective object with a cloud optical depth greater than 3. And I'm going to be referring back to these thin and thick cloud fractions throughout the remainder of this presentation. On a cloud object scale, we see that again, the top panel is a vertical reflectivity profile of a convective object, and then the middle panel is showing the long wave, short wave, and net cloud radiative effect. And then the bottom panel is showing in red the cloud optical depth. And it's probably rather hard to see, but there's a dashed line in the bottom panel that corresponds to a cloud optical depth of about 3. And I just want to highlight the regions where the cloud optical depth is, or the net radiative effect is negative. So the short wave exceeds the long wave, and that corresponds to cloud optical depth goes over this 3 threshold.
This is a really dumb question, like cloud optical depth, how is that defined, like at what wavelength?
So that is based on the emissivity. I believe it's defined by the emissivity of the cloud. And we use a Calypso LiDAR for defining it. This is a shortwave.
Okay,
Yeah, shortwave. Yeah.
Okay.
Yeah.
Okay.
Yeah. I had to also remember if I was using shortwave long. Yeah, it's shortwave. Yeah. Yeah.
And is this, sorry, I can't quite see.
Oh, yeah.
Is this actual data or are those lines like that to like show it's kind of schematic?
Oh, this is actual data.
Sorry, on the left side.
Oh, on the left side?
Yeah.
Oh, so this is a simulator, so it's not actual data. Yeah, yeah. And I got this figure is a personal communication with Blas, who does a lot of work with studying the shortwave impacts of these anvils. So then, what do the different cloud thicknesses look like for the full distribution of these deep convective objects? This figure is at first a lot, but I'll walk through it. On the y-axis, we have the long wave cloud radiative effect, and the x-axis, we have the short wave. And then these contoured lines, black contoured lines, signify the 10% all the way up to 90 percentile of the distribution of the deep convective systems. And this black dashed line is showing just like the 1-to-1. So if the convective object falls on the dashed line, then it's contributing a neutral effect. And so then the distribution is colored by the fraction of a convective object with a thin cloud divided by the fraction of convective object with thick cloud. So I'll show you that the bluer, the deep blue corresponds to a convective object with mostly thick cloud. The deep red is mostly thin cloud. And again, so the two regimes then, these thick cloud convective objects in the blue circle here, we see that they primarily contribute a cooling. They have both enhanced shortwave and enhanced long wave, but their shortwave component is greater. And then for the thin cloud objects, we see that they contribute a kind of a weakened cooling and perhaps even a warming that the long wave component surpasses. Yeah, the short wave. And so this is all good, but now how does, cloud top height? Yeah.
Is this only, like the last figure was only high clouds? Is this only high clouds?
Yes, this is only high clouds. Yeah. So we define the high clouds being above 8 kilometers in the atmosphere. Yeah. And so, how does cloud top height come into the story? So these figures, again, reorienting these thin and thick cloud fractions, so now they're on the x-axis with the primarily thick cloud being on the left and primarily thin cloud on the right of the x-axis, and then the cloud top height is in the y-axis. And so we'll just start with the single cell systems. For the long wave cloud radiative effect, we see that it's most enhanced when cloud tops are highest in the atmosphere, and then when also they have mostly thick cloud. Short wave is pretty much when they just have thick cloud and it starts to decrease, or the short wave is weakened when there's more thin cloud present in a convective object. And then the net, we see that they systems that have low cloud top heights, thick cloud primarily contributes a cooling, whereas high thin clouds like cirrus primarily contribute warming. So again, this is kind of like what we learn in fundamental radiation and like cloud physics classes. Multi-cell systems, they kind of exhibit the same behavior. But now we want to understand how do these cloud properties and their radiative effects vary when sorting by the vertical convective intensity of deep convective cores. Yeah. So how do we define the convective intensity of a core? In observations from satellite observations, we don't have a direct way of measuring the updraft speed, the vertical velocity of these convective cores. And so we have to go through a more indirect approach for doing that. And so how we do that is by using the radar reflectivity profiles themselves and calculating the average height of the highest radar reflectivities. And so that's the center of mass or the center of gravity of these deep convective cores. And then we subtract the center of gravity of these deep convective cores we subtract the freezing level from the center of gravity. And that's just to really show the strength of these largest hydrometeors that are being wafted into the atmosphere. So this figure here on the right shows, or I guess on the left here, this is a composite of several convective object radar reflectivity profiles that are sorted by a center of gravity between 1 to 1.5 kilometers. That's considered a weak center of gravity, because that means that the bulk mass of the cloud is just 1 kilometer above the freezing level. Whereas on the right-hand side, we see that the bulk mass of the cloud is greater than 3 kilometers above the freezing level. And so generally, we're seeing much higher reflectivities, higher in the atmosphere, so they're just much deeper in the atmosphere. So now, when we sort so that the distribution by the relative center of gravity, or RCOG, with the with the left figure showing the weakest center of gravity, or weakest intensity regime, and the right panel showing the strongest intensity regime, we see that the distribution does in fact change with increasing intensity, statistically speaking. So the distribution tends to move a little bit more towards this one-to-one line and extend a little bit over the line. And also I want to note that it seems to be that there's an elongation or the larger spread in the thin and thick cloud ratios themselves too. And just to kind of like further clarify that, let's take the distribution, the counts of the most intense systems minus the weakest systems, and then create a difference in these normalized counts. The green corresponds to where the most intense distribution occurs, and the purple is the least intense. And we see that let's see here. As convective intensity increases between these populations, the long wave definitely outweighs the short wave radiative effect. It essentially just shifts the full distribution towards the weakened cooling and slight warming line here, or over this line a little bit. And in this like thick cloud regime, we have both more enhanced long wave and short wave values. And then in the thin cloud region, we predominantly have a reduction in these short wave cloud radiative effect values. So essentially, it's just there's a greater variability in cloud thickness amounts as convective intensity increases. And so then when we take a look at these, the multi-cell cases, when sorting by intensity, we see similar behavior as for the single cell systems. When subtracting from the most intense and the least intense, we see that generally the shortwave cloud radiative effect decreases. And that's likely due to generally an increased thin cloud at the expense of thick cloud. It's kind of hard to tell in these here, but there's slightly more thin cloud in these most intense cases. And it's a little bit also challenging to figure out why that may be the case. It could be that, from the beginning of the talk when I showed that there's a lot of thin cloud that can be present in these multi-cell systems. It could be merging a lot of these intense systems. It would be interesting to go a little bit deeper into the exact processes of what is causing the cloud amount to change. Anyway, so then the long wave increase is not as noticeable, but just to talk a little bit more about my ongoing work, we can then look at how does a long wave cloud radiative effect outweigh the short, if it does outweigh the short wave in all of these thermodynamic and dynamic environments. And this is for single cell systems only, but we can sort these convective objects into the large scale dynamical regimes by the omega 500 hectopascal vertical motion, or the vertical motion from there too. And then also looking at the thermodynamics, we just kind of sort them based on the monthly mean sea surface temperatures. And so this is a heat map here showing on the y-axis, we have systems that are in the descending, weak, and ascending regimes. And then on the x-axis, we have going from cold to warm. And then each box indicates the change in the net cloud radiative effect with an increase in convective intensity. And we see that there is a positive net cloud radiative effect change. So as systems get more intense, they contribute a greater warming in all environmental regimes. And that's because these cloud top heights are getting higher in the atmosphere as they're increasing in intensity. So then just another aspect of work that I'm continuing to do is understanding the life cycle of these deep convective systems and what their radiative effects are. So there's a paper by Unenhaus that talks about how the anvil extent from the parent convective cores is a signature of the life stage of convection. So the you know, more mature systems and even in the decay stage, they have these really long, extensive anvils that you know, can span last for hours even after any sort of deep convective core is after that any deep convection dies away. So this plot here shows again a distribution, but instead of colored by cloud thickness fractions, it's colored by the length scale or the lengths of these convective objects, and we can perhaps try to map out the life cycle of convective systems based on their length scales. And if you remember, the thin cloud, the systems composed of primarily thin cloud fall in the same region as where the length scales are largest. So I'm assuming that this is the decay stage of deep convective systems. But
Yeah, so as you're thinking about the life cycle, are you going to be
Mhm.
limiting similarly to only deep convective clouds, or will you consider, transient congestus mode as well?
Yeah, I think it would be important to consider the transient congestus mode. And yeah, because this whole study is really just focusing on the active, let's say, or the mature stage of deep convection. And transient is definitely important to include. And this is also limited because we're only looking at, I think there's a lot of, great things that we can get out of it, but because we're initializing that we have to find or identify a deep convective core to begin with, we're not able to perhaps capture convective initiation or essentially the decay or dissipating stage of convection. So yeah. But kind of a follow on for that, we can perhaps make use of another data set that has more temporal evolution, such as geostationary satellite observations. And so I've begun work on co-locating these convective objects with a tracking algorithm for identifying and tracking MCSs. And so each, I guess, blob here shows evolution of an MCS, and at every time they're assigned a different life stage. So, I'm finishing up this work and making this convective object database available, and it will be made publicly available on the CloudSat Data Processing Center soon. And then also, it's really exciting to think about how can this work be useful for useful to the fields, for example, evaluating K-scale models that are now able to resolve systems on a convective or on a convective scale. And then also being able to use these cloud and precipitation tracking methods in combination with this database such as this. And there's actually going to be a workshop here at the end of April looking at these cloud tracking methods that I'm working on helping organize along with Greg Elsasser and then some other folks. And this will all be useful for upcoming missions such as GISS, which is going to be looking a lot at these convective updraft regions, Earth Care, and also the atmospheric observing system too, hopefully. So just to summarize this work, I showed that deconvection is rather infrequent, and it contributes to small net cooling at the top of the atmosphere. However, the cooling weakens as the convective intensity increases, and that is predominantly due to an increased cloud top height for single cell systems. And then we also have more work to be done is looking actually at the radiative effects of the cloud component. So with the cloud optical depth of 1 to 3, because actually that region is important too, like that the cloud optical depth of 1 to 3, those clouds actually generally contribute a warming. So how are those, what are their radiative effects and how much do they take up in the convective object? And then more analysis on the large scale environmental influences and capturing the life cycle of these systems. So now switching gears a little bit, I'll be just presenting 2 slides on my postdoc work. And I was really excited. I forgot to put the label of CloudSat Calypso on this slide, but anyway, I was excited to get this opportunity here at GISS because I think this work is a nice follow-on, and actually I'll be looking at trying to calculate these high cloud feedbacks in observations and apply them to models. And I really want to learn at the center just how to better think in a modeling framework and how observations can be used for models. So I'm working with Greg Susanna, but then this work is also in collaboration with Thibaut Vaillant-de-Guélis, and then Asia Aruf, Andrew Ackerman, and Anne Fridland. So just a little bit of a motivation for this work. Climate models, they do not adequately portray the top of atmospheric long wave high cloud feedback, which was work that Thibaut showed using Calypso measurements from GeoCCP, or from the LiDAR with a product called GeoCCP. And this work was neat in that they were able to decompose the different high cloud contributions to the long wave cloud feedback. And so C opaque is the opaque high cloud cover. ZT opaque is the depth of or the cloud altitude of these opaque clouds. And then we have thin cover, altitude of thin clouds, and then the thin cloud emissivity. And this figure is showing that model simulations tend to overestimate these changes in high cloud top heights to the cloud feedbacks. But what we should actually be studying more perhaps is how the high cloud cover is changing per degree surface warming, and what those contributions are to the long wave cloud feedback. And so my work will be kind of expanding on this notion by first identifying and isolating different high cloud types, so stratiform, convection, anvil, and then their different high cloud properties. And then also evaluating the sensitivity of high cloud changes to local environmental conditions or cloud controlling factors. So think features such as sea surface temperature. This figure is showing different cloud controlling factors that would influence deep convection. So upper tropospheric stability is important, same as relative humidity at different layers in the atmosphere, vertical wind shear. And then the figures on the right show plots of the total long wave cloud feedback on a shorter interannual time scale, derived or calculated from series and Calypso GeoCCP observations. I just updated them from previous work that Greg has done, but ultimately we want to calculate long wave, short wave, and net short-term and long-term high cloud feedbacks. So that concludes, and thank you so much for attending.
We definitely have a few minutes for questions, so.
Near the beginning, you had the slide where you got these hundreds per meter square shortwave and long wave effects, and all canceled to 1.28
Oh, yeah.
meter square.
Yeah.
Is this similar to the retrieval-based stuff in much of your presentation, or? Okay.
Yeah.
I would, I mean, I guess this is encountered a lot in these kind of cloud things, that you get these really strong effects, but then they cancel very heavily,
Yeah.
which I find deeply worrying to look at. So I wonder, could the uncertainties be at least the order of magnitude of the measurement? But then also, I don't know which clouds you include here, right? You mentioned for some of the others, you included only above 8 kilometers.
Yeah.
If you included 7 kilometers, if you had different criteria for counting
Yeah.
in like subvisible cirrus and things, could it be a ill-posed problem where just like little changes to what you represent would totally change the answer?
That's a good question. Yeah. Well, so the reason why we chose, clouds with at least above 8 kilometers was it was very physically based in looking at the actually looking at the shortwave cloud radiative effect, because we are seeing that for clouds below 8 kilometers, their shortwave was not, the cloud radiative effect was not changing even as cloud, the amount of thick clouds increased in these objects, and that has to do with the fact that we are likely looking at systems with a lot of liquid water, and so those have different radiative interaction or shortwave radiative interaction. So that was more of a physical constraint that we put into this analysis. But I do think like going a bit deeper into the uncertainties would be important. However, like I think we're also looking at so many different systems from this statistical standpoint. I don't know, how much it would change, but that's a good point. Yeah.
I have a question. You define the center of mass, but you actually weighting by the reflectivity.
Yes. Yeah.
So maybe the reflectivity is not, if the droplets are different sizes, it might affect the reflectivity more so than the mass. And so is there like, do you account for this bias somehow? Or you just assume that in general, all the deep convective objects have the same size distribution in terms of droplets?
Yeah, so it is just kind of an assumption of that all droplets are roughly the same size, but the thing is that in these, we're only looking at the center of gravity in each deep convective core region, so that's where the most, like the highest reflectivity values are located anyway. So there is kind of an assumption that all of these core regions, I think, have just like really large precipitation size droplets in them. But
I don't think it's mass, it's gravity, so it's like not like actual like center of mass, but just like
it's
like just where the most reflectivity was found as a proxy for convective intensity.
Okay, because maybe a best bit for the test that I'm studying, like the larger the test, the smaller the reflectivity. So if you want to look at the center of mass or the center of optical thickness or reflectivity, it will be very different because the small particles tend to be much higher than the large ones.
Yeah, I was gonna ask something similar about like the center of gravity thing, because I know that it is kind of a pitfall, or not pitfall, but like it's a proxy for convective intensity, but
Yeah.
what are the pitfalls of trying to use it? Because like clearly, we haven't found, and GISS is like trying to like make strides on that and
Yeah.
increasing our like observations of convection. So did you like through the research that you did, like did you find like kind of weaknesses in just using the center of gravity as a proxy for convection intensity?
Before you into that, there's also a very relevant question on the same topic from Greg Sasser in the
Okay.
chat. He said, Juliet, nice talk. Is there a reason why center of gravity would be better than echo top height for intensity? The latter is not as affected by attenuation within the cloud. So maybe you can address both of those questions.
Yeah. So. Yeah, that is a good point, that attenuation is, well, let's see here. I feel like I don't have a good, I don't have a good answer for that necessarily, other than the fact that this center of gravity also can take into account perhaps differences between the high cloud top and the echo top. Let's see. Yeah, I can't, sorry. I don't quite have a good answer for that one. I think the pitfall, I haven't found, I was doing a comparison of calculating the center of gravity, actually, at the point where the highest reflectivity value is located, and then just the center of gravity with the full column, and I did not notice a large difference in comparing magnitudes of intensities between accounting for attenuation and not accounting for attenuation. But I think it is a really good idea to look at a little bit the differences in the center of gravity and echo top height calculations and being able to capture intensity. And that actually is work being done by Hani Takahashi, who's evaluating a lot of these different convective core intensity and mass flux methods. But yeah.
So you're looking at the cloud feedback in the end, watts per meter squared per meter EK. So where is your temperature change coming from? Is that like a trend over the 17-year record or the?
Yeah, so the temperature is a global surface temperature mean anomaly. It's an anomaly, yeah, over the whatever record we're looking at. So first, just this intraannual scale is over a 10-year time period. And then ultimately it would be nice to capture a more climate, temperature trend.
You were to like aliasing due to events or something. I mean,
yeah. Yeah, I think that definitely, well, okay, so we deseasonalize them, but yeah, I don't know, Greg, Susanna, if you're still on, would like the El Nino or La Nina come into play?
I'm not sure. Were you saying that can we reproduce a specific event?
That you showed on Seaboard, we did it between 2008 and 2014, and the El Nino 2010 was not that intense. We didn't impact good result. Then he looked at El Nino effect in 2016, which was really a big El Nino, and yeah, it has an effect on the top of the atmosphere, relative effect of the feedback. And to come out from the natural variability, I think we need at least 13 years of observation, and we don't have that with active sensor for now. So we can combine the satellite, the Calypso LiDAR and the radar with future missions to have like 13 years and be able to come out from the natural variability.
Okay, thanks.
Okay, I think we'll make this the last question.
Well, it's a question and a comment. At the beginning, you show, shortwave and longwave CRE as a function of optical depth. But then you stop at an optical depth of about 6.
Yeah.
And your shortwave keeps increasing,
Yeah.
your longwave has saturated. However, if you go to even higher optical depths, eventually your shortwave is also going to saturate. And the objects you're looking at have fairly high optical depth. This is the reason why stronger updrafts, the change in cloud top pressure takes over, because the systems are already thick enough, and they do change their optical depth, but their albedo doesn't change very much. So stopping this at 6 is whatever you're stopping it is a little confusing, because you're looking mostly at systems with optical depths much higher than 6 anyway. So that, I think that confuses your interpretations a little bit. And the other thing to be careful is, and it goes to Zachary's point, is when you're looking at TOA and you say balances, long wave and short wave balance, one thing you always have to keep in mind is that short wave is usually manifested as a cooling at the surface. Long wave is manifested as a warming in the atmospheric column, middle to top of the troposphere. So you can have an atmosphere where you cool the surface by 10 watts per meter square, you warm the upper troposphere by 10 watts per meter square. This is, you can say it's a zero balance atmosphere, but that's going to be a very different world than the one you came from. I mean, the fact that they balance at the top doesn't mean that there's no other feedback processes that are going on, because they manifest, shortwave and longwave manifest themselves at different parts of the atmospheric column. So
Yeah, absolutely. And I think another aspect of that is definitely considering the radiative heating and cooling of the atmosphere from these clouds. I agree. Good point. Thank you.
Okay, I think we can end it there. We have another round of applause for Juliet. Thank you. And you're here at GISS, so people can stop by and chat if they have more questions.
So I want to please.